Today we are discussing example of a two-component system having one melting point. We have already discussed in my earlier session about the two-component system having one congruent melting point. That's why today I am giving you just one example of such system. The example is zinc magnesium system. You can see the phase diagram of this system. In the left side, pure zinc. The melting point of pure zinc is 419 degrees Celsius at constant atmospheric pressure. And from left to right, percentage of magnesium increases, and this is 100% magnesium. And the melting point of magnesium is 651 degrees Celsius. This is the congruent melting point, 575 degrees Celsius. The composition is nearly 20% of magnesium and 80% of zinc. This is eutectic point, and there is another eutectic point. The new compound formed having congruent melting point is MgZn2. This is a new compound which has the melting point at this point, that is 575 degrees Celsius. This type of system has already discussed. Now I am going to tell you about the example of two-component system having more than one congruent melting point. Formation of more than one compound with more than one congruent melting point. When more than one compound is formed in a two-component system, the number of humps will also be greater. In the earlier discussion, you have seen just one hump. Now, I am going to tell you about the two-component system which has more than one hump. The example of such system is Fe2Cl6 H2O system. This is the phase diagram of such system. Water is in pure form, and this here pure Fe2Cl6. At normal atmospheric pressure, that is 1 atm, freezing point of pure water is just 0 degrees Celsius, which is represented by point A. You can see there are 4 humps, that is 4 congruent melting points. Along AB, the freezing point of water decreases due to addition of more and more Fe2Cl6. This here composition increases, that is moles of Fe2Cl6 increases. At point C, a new compound Fe2Cl6 12H2O. This is called dodecahydrate is formed. So this temperature at C point, the temperature at this point is called congruent melting point. Why it is congruent? Because beyond this C point, no Fe2Cl6 12H2 exists. At this point, only solution of water and Fe2Cl6 exists. On lowering the temperature, the solution is just cools down. at point C, Fe2Cl612H2 in solid form just exists, and it is remained in equilibrium with the solution. Below C point, just about on the vertical line, only solid Fe2Cl612H2, that is dodecahydrate, exists. No solution exists below this C point about the vertical line. The temperature at this C point is 37 degrees Celsius. That is, the congruent melting point of dodecahydrate is 37 degrees Celsius. On lowering the temperature along this line, CB line, the congruent melting point decreases about we may also call this CB line the solubility curve of dodecahydrate. At this point, three phases coexist. That is ice, dodecahydrate, and the solution. Hence, it is the eutectic point of the system. Since ice exists at B point, the point is also called cryohydric point. Therefore, it is the eutectic point which is called cryohydric point because ice exists at this point. The degree of freedom at this point is 0 at constant atmospheric pressure. On addition of Fe2Cl6, the congruent melting point again decreases along CD line. Along CB line, congruent melting point decreases due to addition of water, and along CD line, it decreases due to addition of Fe2Cl6. That is, Fe2Cl612H2O, that is dodecahydrate, has two types of solubility at a definite temperature. This type of solubility is called retroflex solubility. Retroflex solubility. Hence, we may come to a conclusion that at a definite temperature, the dodecahydrate has two solubilities. This type of solubility is called retroflex solubility. At point E, another new compound emerges, and this is Fe2Cl6 7H2O. It is called heptahydrate. Hence, D is another eutectic point where dodecahydrate, heptahydrate, and the solution coexist. But this is not cryohydric point because ice does not exist at this point. Hence, it is only an eutectic point. Therefore, E is another congruent melting point which is 32.5 degrees Celsius. G is another congruent melting point which is 56 degrees Celsius, and at this point another new compound Fe2Cl6 5H2O exists. This is called pentahydrate. Therefore, F is another eutectic point where heptahydrate, pentahydrate, and the solution exist. Again, I is another congruent melting point. Fe2Cl6 4H2O, that is tetrahydrate, exists. Therefore, H is again another eutectic point where pentahydrate, tetrahydrate, and the solution coexist. Therefore, there are 4 congruent melting points and 1, 2, 3, 4 and 5 eutectic points. Among the 5 eutectic points, B is called cryohydric point because ice can exist at this point. The other 4 eutectic points are normally called as eutectic points. At point J, it is another eutectic point. At point J, tetrahydrate solution and anhydrous Fe2Cl6 coexist. Beyond this point, only anhydrous Fe2Cl6 can exist. And this is extended with a dotted line. Beyond this curve, only dilute solution exists. Beyond this curve. In that area, ABM, ice and the solution are remained in equilibrium. At this region, C, B and N, at this region, dodecahydrate and the solution remains in equilibrium. Below this line, MBN, only solid ice and the solid dodecahydrate coexist. In the region COD, in that region, COD, dodecahydrate and the solution coexist. In that region, E, D and P, EDP, in that region, heptahydrate and the solution coexist. Below this line, ODP, below this line, dodecahydrate and the heptahydrate coexist. In that region, EQF, heptahydrate and the solution coexist, that is, they remain in equilibrium. In that region, GFR, in that region, pentahydrate and the solution remain in equilibrium. And below this line, PFR, heptahydrate and pentahydrate coexist. In that region, GSH, in that region, GSH, pentahydrate and the solution coexist. In that region, IH, and up to this point, in that region, tetrahydrate and the solution coexist. Below this line, extended SH, below this line, pentahydrate and tetrahydrate as solid form. In that region, ITJ, tetrahydrate and the solution coexist. And beyond this J point, that is in that area, only the Fe2Cl6 and the water coexist. The Kj is the solubility curve of anhydrous Fe2Cl6. And below this line, TJL, anhydrous Fe2Cl6 and the tetrahydrate coexist. Let the solution is isothermally evaporated from a point A. Isothermally means the temperature of the system remains constant. The solution is just heated at a constant temperature at point A at constant atmospheric pressure. At point A, it is dilute solution of Fe2Cl6. Point A to B, unsaturated solution of ferric chloride. At point B, just the solid form of dodecahydrate starts to commence. Going from B to D, more and more of dodecahydrate separates. Composition of the liquid remains unchanged. Just the volume of the solution decreases on moving from B to D. At point D, the solution completely disappears and the system consists of only the solid dodecahydrate. At this point, only solid dodecahydrate exists. The solution completely disappears. From D to E, that is on going from D to E, more and more solution is produced and less solid is left. At point E, the solid dodecahydrate just disappears, and on going from E to F, the solution becomes unsaturated. That is, beyond E point, the solution becomes again unsaturated. At point F, the heptahydrate starts to separate. On going from F to G, more and more heptahydrate separates out from the solution and the volume of the solution decreases gradually from F to G. At point G, complete solidification of heptahydrate occurs and the solution just disappears. On moving from G to H, solution reappears and the solid heptahydrate decreases. That is, the amount decreases and the volume of the solution again increases on going from G to H. Like this way, at point J, only solid pentahydrate appears and the solution disappears completely. On moving from J to K, that is along the JK line, the transformation of pentahydrate to tetrahydrate occurs gradually. That is, on going from J to K, more and more pentahydrate transforms to tetrahydrate. At point K, complete formation of solid tetrahydrate occurs. That is, at this point we have only the solid tetrahydrate. On going from K to L, transformation of tetrahydrate to anhydrous salt, that is anhydrous Fe2Cl6 occurs, and on going from K to L, more and more tetrahydrate is getting converted into anhydrous form. If the evaporation is continued, then ultimately one can get the pure anhydrous salt. That is, on going from the right side completely, we can get ultimately the pure anhydrous salt Fe2Cl6. Therefore, from this phase diagram, we have learned more than one congruent melting points. In this phase diagram, we have just 4 congruent melting points, and there are many examples where more than 4 congruent melting point occurs, and also 5 eutectic points. One of these eutectic points, the first one, that is the first one, first B, is called cryohydric point. This is enough for today. In the next session, I will discuss about the incongruent melting point and the related phase diagrams. Thank you.